midterm 1 through today. Okay, so it'll cover focusing on strengthening mechanisms and fracture, fatigue, and credence. Okay, there won't be any viscoelasticity per se on the midterm. Okay, and some of that, true stress, true strain, injury, that's all before. So I'll send out a review sheet with the topics, but strengthening mechanisms require you to remember things about dislocations, right? So it's not like you can't forget about dislocations and just do strengthening mechanisms. You have to know definitions of stress and strain and those type of things. So I'll send out a review sheet with that. Try to get that done today. If not, I'll definitely do it this weekend. So you'll have it to go through and look at that. And then, the final is the whole exam. There will be viscoelasticity on the final. Okay. There will be probably true stress versus engineering stress on the final. So the final is comprehensive. The midterm 2 is just since midterm 1.
And will the final be double the length of the midterm, or should we expect to be the length of the midterm?
Yeah, it's 2 hours, right? Yeah, it's your normal, I guess 8:30 to 10:30 in this room on Tuesday. So yeah, so definitely 2 hours.
What date is it?
The
The 25th.
It's the 26th, correct? The date.
The date of the final?
No,
Of today.
Today, I think, is the 26th.
Yeah.
Yes.
Thank you.
Does it
Sorry.
matter?
For my notes, yes.
Oh, for your notes, okay. All right. So we'll see so midterm will be in a week on Friday. I'll definitely get you out a review sheet for that. The homework's due on Wednesday. We'll get the solutions to the homework up, I guess probably Wednesday night. Then that's either Wednesday night or Thursday morning, but then there'd be no late homework, which usually not an issue. So you'll have those to study the solutions for the midterm. Anything else on logistics, class organizations? Okay, so now we're moving on from fatigue, where we had cyclic stresses, which can be at a variety of different temperatures, but the main driving effect is that you have a cyclic stress. So looking at high temperature failures, and this is mostly going to be what we call creep. So if we just start with a stress strain curve, and we compare room temperature behavior, where it goes up, it yields, plastically deforms, and then fails. So that would be room temp to high temperature. Okay. What happens to elastic modulus? Yeah, slight decrease. And again, it depends on the material. For metals, modulus may decrease 5-10% with temperature. A polymer, if you go through TG, your modulus changes by 2 or 3 orders of magnitude, thousands of times. So it depends. So if we look at a metal, it would be a very slight change in modulus. What happens to yield strength? Is it easier for dislocations to move at high temperature or low temperature? High temperature. So it's easier for dislocations to move. Yield strength goes down. So generally, yield strength significantly decreases with temperature. What about strain hardening? What is strain hardening? Strain hardening is where dislocations run into each other and pile up, and it's harder to keep things moving. At high temperature, what can happen? Hot rolling versus cold rolling. You can get recrystallization, you can get dislocations rearranging and get recovery. So dislocations are mobile at high temperature. So they don't run into each other and stay stuck as much. So like traffic in a snowstorm versus traffic on a sunny day, right? Cars are your dislocations. In snowstorms and cold temperatures, traffic's terrible. Okay, a lot of work hardening. Okay, but you can move, so you don't get as much strain hardening. So this is the amount of strain hardening, right? So you don't get as much strain hardening, but you tend to get more ductility, and it may go like that. So this is that high temp. So what's high temperature? $1,000 room temperature.
2/3 the melting point.
So it's related to the melting point. Yes. So it's relative term, right? High temperature for plastic is not high temperature for steel. High temperature for aluminum is much lower than high temperature of steel. So high temp. High temp is where temperature is greater than, that's actually, the more generic is where temperature is high enough to change deformation and strengthening mechanisms in this case, right? And what does that generally mean? It can be atom and molecule mobility is thermally enhanced. Okay, so now temperature is allowing the, when you're stressing something, you're moving the atoms, right? And then you plasticate a form of dislocations are moving, that's moving the atoms. If temperature is affecting that, then that would be sort of a definition of high temperature. Typically, we're saying for crystals, temperatures greater than or equal to about 0.3 to 0.4 T melt in absolute units. So degrees K, or if you're in Fahrenheit, you'd use Rankine. We're not doing that, right? So in degrees K. So 273, right, is 0 C. 293 is room temperature. Okay, so in absolute units, for crystals, if temperature is greater than that, for amorphous materials, what's T melt? There isn't one, right? Melting, the thermodynamic definition, is going from an ordered state to a disordered state, right? If you're already disordered for an amorphous material, you can't melt it thermodynamically. Okay, it's dripping, it's fluid-like, okay, so it's a frozen liquid going to a mobile liquid. So for amorphous materials, the important parameter is Tg. So at temperatures greater than Tg. So that's our definition of high temperature. So we're talking about where these things happen, where we see that change in behaviors, is temperatures greater than 0.3 to 0.4 T melt, or temperatures greater than Tg. Tg, you go from molecules being locked in, you heat them up, the molecules are now mobile and can slide past each other. So temperature affected the mobility. T above 0.3, 0.4 T melts in crystals, what happens there? diffusion becomes significant at high temperatures, right? That's atoms moving. So now you can have atoms moving from two different effects: diffusion and stress. Stress, makes dislocations move. Okay, diffusion has atoms move by hopping from position to position to position. You do that enough, you'll change the shape of your particle. And those can be combined. So that's what happens at high temperature. And both of these are time dependent behavior. So for amorphous, we get viscous flow, right? That's what we learned about viscoelastic behavior. Remember when you were below TG, everything was just elastic? You went above TG, then you changed your model and you would include the dash pots where you get viscosity and all that time-dependent behavior. Okay, that's high temperature. That's creep. Remember we read there was a stress relaxation experiment and a creep experiment back in the viscoelastic reading. Okay, so I sort of touched on that. We're not going to be going through all the models for that because we sort of talked about that for polymers. So most of the creep we're going to talk about today is for crystals. So for crystals, which I'm generally talking metals and ceramics, time-dependent behavior, we now get diffusion. And diffusion can have several effects. It can enhance dislocation motion. So two dislocations run into each other and they get stuck. Well, if they do a little bit of rearrangement here, they can slide past each other. Okay? So enhanced dislocation motion, this can either be recovery type things. It can be recrystallization. Remember, during annealing, recrystallization occurs by diffusion. Grain growth occurs by diffusion. So all those can be combined with stress to affect high temperature behavior, but all of these are time-dependent phenomena, right? They don't happen like this. It's not the Martin-Siddick phase transformation. It's atoms jumping from place to place to place, and that takes time. And you can just, that diffusion itself can transfer mass. So those are the time-dependent things we're going to talk about and how that affects our high temperature behavior over long times. So we will talk about creep. And this is a sustained load at high temperature. So typically you show some support, some sample on it, you put some load P on this, okay, and you start off with some initial length, L naught. After time, you now have some L of I, which could be your initial, and you still have your P on it. So this has gone through some delta L, some change in length over time. So I obviously, since different lengths of material would have different L's, you look at strain, so delta L over L versus time. And that's how you characterize your creep behavior. So if we plot strain versus time, okay, here's time 0, which is when we put the load on the piece. What happens when you put a load on a part? Elastic stretching, right? Elastic deformation. So you get an instantaneous deformation, which is just the elastic part, the same thing you'd get at low temperature. Just stress is elastic modulus times strain. Strain is stress divided by modulus, right? Elastic stretching. But as you hold it there, now things can start moving around. And you could even go, it's instantaneous deformation. It could be beyond the yield strength. Still, you stretch to some level due to that load. You then will get time-dependent behavior. It usually does something like this and does that. So there's 3 stages of creep. There is your instantaneous deformation, and usually it's just elastic because the stress you're applying is less than sigma yield, right? In this region, it's called primary creep. In this region, from here to here, it's called steady state creep. And then from here to here is called final, or usually tertiary creep. Well, I'll even say, because fracture. What happens when your strain starts doing this? Eventually it breaks, right? So that's where you get fracture. So those are the 3 things. Sometimes they call this phase 1, phase 2, and phase 3 creep, tertiary creep.
So is the instantaneous not part of that phase?
It's not permanent deformation.
Okay.
So generally it's sort of, yes, it could be if you want to combine the elastic and plastic deformation, but some people say creep is just plastic deformation. I wouldn't be that picky. So it could be the elastic part, but generally it's the part, it's time dependent. That's sort of a definition of creep, so it's a little bit fuzzy there. So that's a typical creep curve, and this is time dependent, and this is, once you get past here, everything from here above is plastic deformation, permanent deformation. That's just your initial elastic. All this is permanent plastic deformation, shape change of your materials. So there are generally 4 creep in engineering. We see 4, well, say types of failure. These are illustrated in Ashby, but the 4 types these aren't the mechanisms of how they fail, it's the physical ramifications of why it failed. We have displacement, limited applications. So if you have precise dimensions or clearances, think about a turbocharger. Your blades are spinning in that turbocharger and there's an outer shell there. If those blades get too long and hit the outside of the case, turbocharger's gone. Okay, so that would be a displacement limited application. It didn't actually break due to creep, it broke because it got too long and hit something. That's different than other types. You can have rupture limited. An example would be like a pipe bursting. You can have stress stress relaxation. So there was an initial required stress that decreased over time. For example, a bolt is tightened to a certain torque. If that bolt then stretches over time and it's not at that torque anymore and other things now can move because of that, that is a stress relaxation failure. And the fourth is what's known as a buckling failure. And in Ashby, he's got nice pictures of these. I went through them here and roll so you can actually see them. So here's an example of type 1. So your turbine blades, and if those blades get too long and they hit the outer shell there, they'll fracture. This is a more of a rupture limited. So here's a pipe with a pressure and you blow out your pipe. A bolt holding two pieces together, they have to have a certain pressure there to keep those from sliding. Okay, if that bolt loosens because it's stretched over time, you lose your clamping force. Example of an airplane wing, that if it starts deforming here, and again, buckling, remember what buckling is? It can do that, so it starts to deform and then all of a sudden it'll go very fast because it got, the stress is out of plane, so you get buckling limited creep. So those are sort of 4 examples how creep failures can occur. And so now we'll get more back into the mechanics of creep. So that's just Ashby. I think we're in jumping to chapter 17 now in Ashby for creep. So here is, again, the typical curve for creep and the type of behavior we see. Scratched. Okay. So we're looking at creep strain versus time. So this is not a stress strain curve, right? Make sure you don't, draw a stress strain curve. It's creep versus time. Stress is constant in this case. You get your instantaneous deformation, your primary creep, secondary creep, and tertiary creep to fracture. Majority of the life is spent in this secondary creep regime. And so we can look at the creep rate, which is delta strain, delta time. So the slope of this curve is our creep rate. which is also DEDT. So if you look at the instantaneous, it's just the derivative of that, right? And that is often shown as E dot. So remember, a dot over something generally means it's the derivative with respect to time. So, you know, we used it in viscoelasticity, we had gamma dot, that was our shear strain rate. Okay, well, this is just tension in this case. So that's our strain rate. And what they found is you can model this linear behavior. So the creep rate in the phase 2 or the steady state is shown here. So the strain rate is a constant K. Sigma to the n is exponential of minus QRT. So K and n are creep constants. Sigma obviously is stress. E dot is strain rate. Q is an activation energy for creep. Remember diffusion. D is equal to D naught EXP minus Q over RT. Arrhenius type relationships, right? Well familiar, okay, similar thing there. It's not necessarily the same activation energy as for diffusion. It's the activation energy for creep. Okay, but this creep is a diffusion enhanced deformation mechanism. So it's related to the diffusion coefficient, yeah.
Does that equation only work for the secondary region?
Yes. So it's a linear fit. Looking at this, this is where that works. Yeah, so it's for the stage 2. Just remember that. The activation energy for creep. R is your gas constant. So if you look at these effects and we plot creep strain versus time at different temperatures. So here is our sort of typical behavior. What do you think happens if you lower temperature? We keep stress the same, we lower the temperature, and we redraw this curve. Are you going to get more creep stain at a low temperature or less? Less. And maybe even a little bit less elastic deformation because your modulus increases a little bit with temperature. So as you'll get a lower slope, and it can go out to there. What happens if you keep lowering temperature? What if you go below a temperature 0.2 of the melting point? T less than 0.3 T melt. Is this creeping? How much deformation are you getting here? None, no permanent deformation, right? Deformation increases this way. So here, no creep. So as you increase temperatures, you get this type of effect. So there's T1, T2, T3, T4, and T1 is less than T2, is less than T3, is less than T4. So for each of these, you can get a strain rate for 3. Here's our strain rate for 2. What's our strain rate here? This black one? What's DE dt? 0. Okay, so you can see these strain rates at these. So obviously, oops, that's strain rate 4, sorry. So you can see strain rate at temperature 1 is less than strain rate at temperature 2, less than strain rate, oops, at 3, which is less than strain rate at 4. If you look at this for now, this is at same sigma. Now if we look at constant temp and increase stress, strain versus time, okay, there's 1. What happens if you decrease the stress? How's that going to affect this curve? You get the same amount of elastic deformation? If you decrease stress?
If we're. Never mind.
Stress is equal to strain times elastic modulus. Strain is equal to sigma divided by E. This is for Hooke's law, right? The elastic stress. You decrease your stress, you're going to get less elastic deformation, and lower that. As you increase your stress, you'll get more. Okay, so sigma 1, sigma 2, sigma 3, sigma 4. So you can see stress of 1 less than stress at 2, less than stress at 3, less than stress at 4, and you get that same effect here. You can look at your strain rates at those different stresses. Strain rate of 1 is less than strain rate of 2, is less than strain rate of 3, is less than strain rate of 4. So you see that matches our equation here that we came up with, where strain rate for stage 2 is equal to K sigma to the n exp minus Q over RT. You increase stress, you increase strain rate. You increase temperature to the negative exponential, right? Increase strain rate. So those fit. So how do we get these constants? Oftentimes you plot strain rate versus sigma at given temperature. We want to try to simplify this out. So you make a plot log sigma versus log strain rate. You get a slope, a straight line. So this is our data that we measured, our strain rates. Okay, so here's at a given temperature. We measure these strain rates, plot them, strain rate versus temperature, or versus stress. And the slope of this curve is n. Gives you the stress dependence, right? We're changing stress, keeping this constant. This gives you how you find n. And if you look at this at different temperatures, this would be T1, T2, and T3, where, what do you think there is, T1 higher or lower than T3? For a given stress, do you get a higher or lower strain rate at T1 versus T3? The higher strain rate at T3. That should tell you T3 is higher than T1. That make sense? Okay, how do you find Q? Plot strain rate versus 1 over T. So now you have strain rate here, 1 over temperature here. You'll see this. Higher temperatures are here. This is 1 over T, right? Strain rate goes up at higher temperatures, goes down at lower temperatures. So that would be a plot of strain rate versus temperature. Slope of this is proportional to Q, depending where you put your RT when you solve this equation. So this would be, for given stress. You can simplify it and say strain rate is now equal to some constant, E to the minus Q over RT. So this C is now incorporating a constant stress and an N, right? Since you're not changing that. So the slope of that is Q. And that's how you go through and you can experimentally determine the creep parameters that you need to know. You need to know your stress dependence N and the activation energy Q.
Should it be log survey?
Oh, maybe you're right, yes. Because it's the exponential.
Exactly.
So L or Ln, depending whether you want it over 2.3 or not. So yes, thanks for catching that. That will give you the straight line, otherwise it's not going to be straight. Okay, well, I did have it in my notes, I just didn't get it over. Sorry. Glad you're paying attention. Okay, creeps, types of creep failures, environmental effects. Talk about mechanisms. So oftentimes when you see creep data for engineering uses, you'll see plots that look like this. Stress on this axis and rupture lifetime. And you'll get plots that look like this. T1, T2, and T3. So these are creep rupture plots, and so this is where you actually would be looking at strain versus time. That is our rupture lifetime. So if you're designing something where the rupture is the critical failure mode, we looked at those 4 different types of failure. One of them was rupture limited. So like when your steam pipe bursts, that's an issue. If it just comes out a little bit, Yeah, that's not that big of an issue in the heat exchanger. They can change, dimensions aren't critical, it's when the pipe actually breaks is critical. You would use creep rupture lifetimes, so you would know that for a given stress, at a given temperature, you could predict your rupture lifetime. That's how you use creep rupture curves. The other type of curve that you get is a strain rate curve. So that's creep rupture. The other is what we call strain rate curves. And there you plot stress versus strain rate in that phase 2, the steady state creep rate. And you get curves that look like that. And T1, T2, T3. So for a given stress at a given temperature, how fast is it deforming? So you would just go here, come down to there, and then that would give you the strain rate. So, you know, for given stress, temperature, what is strain rate? Then you know you can tolerate certain dimensional change. Say your turbine blade can get 1/10 of an inch longer before it hits the rotor. Okay, so you know that you can calculate that dimensional change. What's the strain you can tolerate in that? It's a 1-inch blade. It can grow 1/10 of an inch. You can have 10% strain before it's going to hit something. You know your strain rate. You now can calculate how long it'll take to get 10% strain. So those are examples of how you can use these two types of curves, and that's typically how, if you look up creep data, you'll see these types of plots, and you need to be able to say, okay, I'm at this temperature and this stress, how long will the life be? Or I'm at this stress and this temperature, or vice versa. How much more life will I get if I lower the operating temperature of my equipment? So if I go from T2 to T3, I will now increase the life and it'll last longer. So you can use these different curves to predict your creep behavior and how things will happen. You know, this is very interested in anything that's operated at high temperature. So a lot of things, jet engines, power plants, furnaces, right? You have your shelves inside your furnace, you're loading them up, they start to slowly sag over time, all of a sudden your parts start falling into each other. You know, there's lots of examples of where creep is important. And so these are typically ways you go through and look at that. Okay, so yeah.
So with fatigue, you have the endurance limit.
Endurance limit in some materials.
So there's some materials that just flat out don't fatigue.
Below a certain stress, they won't fatigue.
Below that point.
Yes.
Is there a similar concept with creep?
Yes.
Oh, okay.
Right? So yeah, below this temperature, or, you know, I guess at stress, if you don't have any high temperature just sitting there with no stress on it, you probably want, you know, but there's always, you can get creep just due to the mass of the piece, right? So, you know, supposedly some of the windows over in Europe are thicker at the bottom than the top now because the glass is flowing down over time. I'm not sure if that's just a urban legend or not, but that would be an example of creep, just due to the weight of the glass. Romans used to use lead pipes, and they would creep. Actually, a lot of people used lead pipes for quite a while, even much past the Romans. And you go over there, and these pipes are doing this between their supports because they have cracked over time. Melting point of lead is, I don't know what, 300 C, something like that. It's not that high. Room temperature, if you look at it in degrees K, lead will creep at room temperature. Solder creeps at room temperature because that is 0.3 to 0.4 of its melting point. Plastics creep at room temperature because if they're above TG. So those are, things where that's occurred. Okay, enough mechanical properties for the day. All right, well, enjoy the weekend. See you Tuesday night, I hope.